today I would like to talk about the difference between Mealy and Moore sequential circuits, and after that, I would like to introduce sequential circuit design. So all of this about sequential circuit analysis. So we have seen many examples about analysis. Let me talk about the difference. So we have two different types of clocked sequential circuits. We have the Mealy machine and we have the Moore machine. Now they are called machines, but they are not really mechanical machines. These are sequential circuits. They are circuits. So in the case of, they are very similar. There is actually a small difference, okay, but very important difference, okay, between these two different sequential circuits. So in the case of a Mealy machine, you can see that here the outputs, which is shown here, the outputs depend on the present state as well as the inputs. So the present states appear at the output of the state register. So the state register here can consist of many flip-flops. So these are flip-flops. We call them state register. And notice that the output here is a combinational logic. So this combinational logic will output the outputs of the sequential circuit. Okay, it will depend on the present state as well as the inputs. We also have a next state combinational logic that will depend on the inputs as well as the present state. So this is how we determine the next state. So in the case of a Mealy, the output depends on the inputs as well as the present state, whereas in the case of a Moore, the output depends on the present state only, and it does not depend on the inputs. So let me write here, this is the present state. So remember that present means that this is the output of the flip-flops. So these state registers here, or this state register, consists of many flip-flops. It consists of many flip-flops, and the outputs of the flip-flops define the present state of the sequential circuit. Notice that the clock here is connected to the flip-flops because they are synchronized. So we are synchronizing the operation of these flip-flops, and the entire sequential circuit, okay, is synchronized with the clock. So changes will happen at the edge of the clock. So this is really the main difference. So when you see the outputs depending only on the present state and they do not depend on the inputs, then we say that this is a Moore type sequential circuit. If you see the outputs depending on the present state as well as the inputs, then we say it's a Mealy type. That's the main difference. This is really the difference between Mealy and Moore. I'm going to show you an example about each one of these different types of sequential circuits. Let me start with Mealy. So this is the Mealy sequential circuit. Notice that we have the state register here in between. These are the flip-flops. They are synchronized with the clock. We have two combinational logic. We have combinational logic for the output, and we have combinational logic for the next state. So the combinational logic for the next state will compute, or will output. It will output the next state. So the next state here appears at the inputs of the state register. So let me write here, this is the next state. So the next state logic is going to determine what should be the values of these flip-flops next clock cycle. And the present state appears at the output. So let me write here present. It means that this is the state now during this cycle. So when you look at the next state combinational logic, okay, we are going to determine what should be the next state, next cycle, okay? So the purpose of this combinational logic is to determine the next state. Whereas the output combinational logic, the purpose is to produce the output of the sequential circuit. So the output here depends on the present state as well as the inputs. Now, the problem with this Mealy sequential circuit is that the outputs are not really truly synchronized with the clock. Notice that the output depends on the inputs, and the inputs can change at any time. The inputs are not really synchronized with the clock. So the present state here is synchronized with the clock. We change the state at the edge of the clock. But because the inputs can change at any time, you might actually have the outputs changing during a given clock cycle. So you might actually get a momentary false values, and these are called glitches. So the glitch is a false output, and you might get it for a short period of time, and then it will go. So that's the meaning of a glitch. And the reason why we get glitches in the case of a Mealy machine is that the inputs can change during the given clock cycle. So this is why the inputs here, so the outputs are not really truly synchronized with the clock. I will give you an example about a Mealy state diagram. So this is a state diagram of a sequential circuit. It consists of 4 states. You can see we have 0, 0. This is 0, 1. We have 1, 0, and we have 1, 1. Now, when you look at this state diagram, how many flip-flops do you have? How many flip-flops do you have, okay, in the sequential circuit? From the state diagram, can you tell? Do you know how many flip-flops? This is a very basic one. How many flip-flops do we have?
1.
1. Any other answer? Why did you say 1? Why did you say 1 flip-flop?
Because in the previous diagram there's only 1 flip-flop.
This 1 flip-flop?
Yes.
No. This is actually, I'm calling it a register. It can have many flip-flops, not just 1. This is not really 1 flip-flop. Okay, it could be many flip-flops. How do you tell this is actually only 1 flip-flop or not? From the state diagram. Hammam, you had actually an answer for that?
2.
Why 2?
4 states.
Is it only because 4 states, or there is another reason? You can see that we have 2 bits inside. We are storing 2 bits. So each state consists of 2 bits. We have 0, 0, we have 0, 1, we have 1, 0, and 1, 1. Now, these actually are stored. These bits are stored in flip-flops. So we have 2 bits, and each flip-flop is capable of storing 1 bit. So clearly, we have 2 flip-flops. Okay? So because we have 2 bits here, then therefore we have 2 flip-flops. If we had 3 bits, then we'll have 3 flip-flops. So it depends on the number of bits that we have inside each state. So in this example, yes, so we have 4 states, so we need 2 bits, and this is why we have 2 flip-flops. So it's not really 1 because we are showing here just 1 state register. The state register, it's called a register because it has many flip-flops inside it. Okay, so that's actually the number of flip-flops. Now notice that we can tell also from the state diagram whether this is Mealy or Moore. Notice that the output here, notice that the arc shows 2 things. It shows the input X and it shows the output Z. And the input X here is 0, the output here is 0. So we have the input, we have slash, we have the output. So the output is shown on the arc. And if the output is shown on the arc, we can say that this is a Mealy. So this is the state diagram for a Mealy sequential circuit because the output depends on the state as well as on the input X. We will see in the case of a Moore sequential circuit that the output depends on the state only, and we draw the state diagram differently. I'm going to show you this next later. Okay, after a few slides, we'll see an example about a Moore state diagram. But this is Mealy, And we know it's Mealy because the output appears on the arc. So each arc is labeled with input/output. And because the output is shown on the arc, then you can say that this is a Mealy state diagram. Okay, it's the state diagram of a Mealy sequential circuit. Now, another thing that we can notice, okay, from this state diagram is state 1,1. Let us take a look at this state, state 1,1. Now, notice that state 1,1, there is no transition to state 1,1. We have transitions out of state 1,1. So from state 0,0, you cannot really reach state 1,1. State 0,1 or state 1,0, there is no transition to state 1,1. So for this reason, we can say that state 1,1 is unreachable. I cannot really reach state 1,1 from any other state. So there is no transition to state 1,1. There is a transition out of state 1,1. So state 1,1 here cannot be reached by the other states, and it is, if you would like, unused. It is an unused state, even though I'm drawing it in the state diagram. We are not really using state 1,1. We are only using 3 states, 0, 0, 0, 1, and 1, 0. From now, state 0, 0 is called my reset state, because if I can have a reset input. Now remember that in the case of flip-flops, flip-flops can use a reset input. So when we reset, we clear the outputs of the flip-flop. So here we have 2 flip-flops, so we can reset both of them at the same time. And when we are resetting them, we are clearing their outputs, so their outputs will become 0, 0. So this is my reset state. So when I reset, I start at state 0, 0. We call it also the start state. Okay, so initially, when you power on a circuit, you don't know in what state you are, because when you connect the flip-flops to a power supply, you don't know what's the initial state. It can be anything. It could be 0 or 1. So for this reason, you need to reset. And here I'm showing the reset here, okay, that will reset and start in state 0, 0. And this is why we call it the start state. Now what we can do is that we can trace a Mealy state diagram. We apply input, we can see what is the next state, and we can check what is the output. So we can draw a table, and this table here will show the time, the clock as cycle here. So I'm showing here the clock as cycles. So initially we start at cycle 0, then cycle 1, etc. So I can show the time at t equal to 0, t equal to 1, and so on. So cycle by cycle. Okay, so I'm showing here the cycles as different columns in this table. I'm showing the input x changing cycle by cycle. So initially x equal to 0, then next cycle it is 1, next cycle it is 1, and so on. Now the state here, we have two bits here, 0, 0. So we can actually name them, for example, A and B. You can call them any name that you want. So here A and B are the outputs of the flip-flops. So what is actually shown inside the circle is the present state, and the present state is the output of the flip-flops. Initially, when you turn on, okay, the power supply, you don't know what is the initial state. So I'm putting question mark, question mark. Yani you can start in state 0, 0, you can start in 0, 1, you can start in 1, 0, or even 1, 1. You don't know what is the initial state. You can reset. You can actually have a reset that will force the initial state to be 0, 0, because when you reset, you are clearing all the flip-flops that you have in a sequential circuit. Right. If we don't know what is the initial state, I'm putting it here as a question mark, question mark. If you are looking at the timing diagram, this will appear in red, for example. If you are simulating a sequential circuit and you don't reset, you might actually see red, indicating that the initial state is unknown. And sometimes you see X appearing. X indicates that this is an unknown output. So this can be the output of a simulator. Right. So if I don't know what is my initial state, I can be anywhere. I can be in 0, 0, I can be in 0, 1, I can be in 1, 0 or 1, 1. If I apply the input x equal to 0, if I am in state 0, 0 and I apply the input 0, this will take me back to state 0, 0. If I am in 0, 1 and my input x is 0, this will also take me to state 0, 0. If I am in 1, 0 and I apply the input x equal to 0, this will also take me to 0, 0. And if I am in 1 and the input x is equal to 0, this will also take me to 0, 0. So it does not really matter, okay, where you are, in what state. So even though the initial state is unknown, if you apply the input x equal to 0, then this will force the next state to be 0, 0 at clock cycle number 1. So remember that the flip-flops are synchronized with the clock. So therefore, they change their output at the edge of the clock. And here I'm showing that the next cycle, at the next state at clock cycle number 1 will be 0, 0. Is this clear? Do you understand this? Now, this is in this specific state diagram. Now, sometimes not all state diagrams are drawn like this. And sometimes if you apply the input 0, this might not really take you back to state 0, 0. So in that case, you have to reset. But in this specific state diagram, if you apply the input x equal to 0, this will take you back to state 0, 0. Okay, is this clear? Fine. Let us say we apply, now at clock cycle number 1, we apply a different input. So the input here is 1. What do you think will be the next state? Well, it is shown in this table, right? So if you are in 0, 0, you are here, and you apply the input 1. Next cycle, you can see the transition appearing in the state diagram. So the transition indicates that next cycle, you will be in state 0, 1. So when you apply the input 1, the next cycle, you will be in state 0, 1. Okay? So this transition will happen at the edge of the clock. If you apply another one at clock cycle number 2, so you are in state 0, 1, you are here, and the input is equal to 1, this will take you to 1, 0. So notice that here, next cycle, this will take me to 1, 0. And so on. So you can trace, you can move from one state to another state cycle by cycle. Now, if you are in state 1, 0, you are here, and the input x is equal to 0, then this will take you back to state 0, 0. So notice that if the input x is equal to 0, this will take me back to state 0, 0, and so on. Now, what about the output? Okay. Now, initially, the output is 0, regardless of the state, because if you are in state 0, 0, or 0, 1, or 1, 0, or 1, 1, if the input x is equal to 0, this is the output here. The output is z. So notice that the output z here is 0. The output here is 0, right? The output here is 0. So, okay, so when the input, so basically here, the output here is 0. The output here is 0. Okay, so if you are in state 1, 0, and the input x is equal to 0, this will be 0, and here the output is 0. Forget about this one. Let me just remove it. Okay, so it does not matter, okay, what is your initial state. You can actually check the output based on the input. So you can see that the output here is 0. But really, the output depends on the state and the input, because this is a Mealy state diagram. So here in state 0, 1, and the input x is equal to 1. So if you are in this state, let me just clean up. No, let me just keep it. So if you are in state 0, 1, so you are in this state, and the input x is equal to 1. So you are actually here in state before that. If you are in state 0, 0, and the input x is equal to 1, okay, so you are in state 0, 0, and the input x is equal to 1, so the output is 0. So you can see the output here is 0. If you are in state 0, 1, you are here, okay, and the input x is equal to 1, then the output is also 0. So you can see the output equal to 0, and so on. If you are in state 1, 0, you are here, and the input x is equal to, so you are here, 1, 0, and the input x equal to 0, the output is also 0. So you can see the output equal to 0. Now notice that if you are in state 1, 0 here, so you are in this state, and the input x is equal to 1, then the output will be equal to 1. So if you have the input x is equal to 1, you got the output equal to 1. So that's when you get the 1 output. The same thing here. You are in state 1, 0, the input x equal to 1, you get the output equal to 1. Okay, so sometimes, even though the present state is unknown initially, sometimes if you apply a certain input like x equal to 0, this will take you back to state 0, 0 regardless of where you started. Okay, so that is the case in this specific state diagram. If this is not the case, then the next state will be unknown. So what you have to do is that you have to reset. Okay, so you have to reset to make sure that you start initially in state 0, 0. Right. So the reason why I showed here question mark is to show to you that sometimes we don't know what's the initial state and you have to reset. Now,
Doctor?
yes, but
Sorry, but regarding the previous table, is the choice of the number is random?
the input x, no. We as designers, we can apply a certain input x to trace and to test our sequential circuit. Okay, so it's not really chosen randomly. We can select our input x. This is called actually is my input x sequence. Okay, to make transitions between these different states. Now, if we don't know what is the initial state, it is safe to reset initially, and then start at 0, 0, and then you start actually moving between these different states. In this example, in this state diagram, my first input was 0 to force transition to state 0, 0 before we start applying inputs. And I applied here the input. Let me just clean up this slide now. Okay, so notice that this input 0 here is to force the transition to state 0, 0. And then after that, we can start applying certain inputs, cycle by cycle. Yani we started by input x equal to 0, then 1, then 1, then 0. And this is to make a transition. So this is x equal to 1, then this will take me from 0, 0 to 0, 1. Then I apply another one. This will take me to 1, 0. Then I apply 0. This will take me back. So basically, you start making transitions, okay, between these different states using the state transitions, okay, then you can test that your sequential circuit is working properly. Okay, so that actually can be used to verify the correctness of your design. I'll talk about design later, okay, on Saturday, but the input x is not to be chosen randomly. If it is given to you, you should be able to determine what should be the state and the output if the input x is given to you, okay, by tracing the state diagram. Right. You can even look at it in, you can look at the timing diagram. So the timing diagram, you can see the signals. Okay, that will be even better than just looking at the table. The table does not really show you the details. The timing diagram will show you even more details. So you can look at the clock. So this is actually the clock, which is a periodic signal. This is my input x. And we can look at the state. The state here is shown by A and B. This is my input x. This is my output z. Okay. Now, initially, the state is unknown. So I'm putting here question mark, because we don't know what's the initial state unless we reset. Okay. Now, one thing about the flip-flops, you can have two different types of flip-flops. You can have flip-flops which use the positive edge of the clock or the negative edge. So you have to look at the types of flip-flops that you are using in your circuit. So here the author is using negative edge triggered flip-flops. I'm just copying this from the textbook. So if you are using the negative edge triggered flip-flops, so depending on the type of flip-flop, if you are using the negative edge, so this is the negative edge of the clock, so all the changes, okay, all the flip-flops are synchronized with the negative edge. So this is very important. First, look at the type of flip-flop that you have in your circuit. Is it positive edge or negative edge? That's number one. Number two, look at the value of the input X just before the edge. So since here we are using the negative edge, look at the value of X just before this falling edge of the clock. So we are looking at the value of X just before the negative edge. That will tell you the value of X. So before the arrival of the edge of the clock, look at the value of X. So here X is equal to 0. This is X is equal to 1. This is 1. This is 0. This is 1. This is 1. This is 1. This is 1. This is 0. As shown here on top. So I'm showing them here, but here you can see that you can see it in the timing diagram very clearly. This is the value of X just before the edge, the negative edge of the clock. So when the input X is equal to 0, this will force the state to become 0, 0. So notice that the change in the state is synchronized because these flip-flops are connected to the clock. So therefore, they change at the negative edge of the clock. So here we start. So when we apply the input X equal to 0, the next cycle after the negative edge, we are changing the state to become 0, 0. Then when you apply X is equal to 1, then this becomes 0, 1. Then next cycle, this becomes 1, 0. Then this becomes 0, 0. Then 0, 1. Then this is 1, 0. And this is, and so on, right? So you can see here, this is actually is 1, 0, okay, etc. So, this is basically is the state, which is represented by two state variables A and B. These are the outputs of the flip-flops. So we can see that we can see how the flip-flops are changing. Now for the output Z, we can look here at the state, and we can look at the input, and then we can figure out what should be the output. So if you are in state 0, 0, and the input X is equal to 1, then the output should be 0. So you can see this is 0. Initially, it's also 0, because regardless of where you start, you will get 0 in this specific state diagram. Now, look here at the state. It is 0, 1, right? So you are here, state 0, 1. So what is the input X? Well, it is 1 during the cycle. So 1 here, it means that the output is 0. So you can see this is 0. Now, this is interesting here. Let us take a look here. Okay, so if you look here during this cycle, notice that X is changing. So X was 1 here, and then it dropped down to 0 during the same cycle. So this is here one cycle between two edges of the clock. This is my clock cycle. That's one clock cycle. So notice that the input X is changing. That's an input. It's not synchronized with the clock. It can change at any time. So the input X is changing during this clock cycle. It was 1, and then it went down to 0. So if you are in state 1, 0, you are here. We are in this state, right? If the input X is equal to 1, then the output should be equal to 1. So notice that once we switch to state 1, 0, the output is going to jump to 1. Why? Because X is equal to 1. But as soon as X drops from 1 to 0, we did not change the state. We are still in the same state, which is 1, 0. We are still in the same state here, which is 1, 0. So as soon as X drops down to 0, then this is going to drop to 0. Notice that here when X is equal to 0, you get different output. So therefore, the output depends not only on the state, but also on the input X. So because it depends on the input X, then you can see that the output is changing during the same cycle. So for this reason, we call this a glitch. So this one here is called a glitch, and we call it a false output. The true output is this 0. That's the true output. Okay, and this is the final output, okay, during this clock cycle. So, so when X becomes 0 here, okay, that's the 0 before the next edge, okay, of the clock, you can see that the output is 0, and this shows the true output. So we got this glitch. So the output jumped from 0 to 1 and then back to 0. So this actually small pulse is called a glitch. It's a false output. You can actually get this false output in the case of a Mealy sequential circuit. okay, because the input is not really synchronized and the output is not really synchronized with the clock. Do you have any question about this? Notice that here we don't really have any glitches. The output here is perfectly 1, this is 1, this is 0, 0. So we don't really have any problem. It's only that we got this glitch, this false output. So it's actually a very, very short pulse. Okay, it's a momentary, okay, it's just actually is a false output for a very short period of time. Now let me talk about the Moore machine. Before that, do you have any question about this? Is this clear? طيب. Let's see this. طيب. So yeah. Let's talk about Moore. What we have seen is a Mealy. In the case of a Moore, okay, the output depends only on the present state. So this is the present state. Remember, the present state appears at the output. The next state appears at the input of the flip-flops. So notice that here the output logic depends only on the present state. It does not depend on the inputs. And because it does not depend on the inputs, we say that the output, so the present state is synchronized with the clock. We change the state with the edge of the clock. And when we change the state, we change the output. So the outputs also are also synchronized with the clock because they depend only on the present state and they do not depend on the inputs. So glitches cannot appear in the case of a Moore machine. Okay, even if the inputs are changing, this does not really affect the outputs. So within a given clock cycle, if the inputs are changing, the outputs will not really change because the outputs do not depend on the inputs. Okay. You can also have a design in which some outputs depend on the inputs and other outputs depend only on the present state. So this is also possible. You can mix. And you can actually have some of the outputs are Moore type and some outputs are Mealy type. So if all the outputs depend on the present state, then this is a pure Moore machine. I have an example about that. This is the Moore state diagram. Now, notice that in the case of a Moore state diagram, you can tell, okay, from the state diagram, this is actually Moore, not Mealy, because the output is shown inside the state. Notice that Z here is the output, and it is shown inside the state. So we have 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. So here we have 2 flip-flops. So we can actually call them A and B. So these are the outputs of the flip-flops. These define the present state inside the circles. Now the output is also shown inside the circle because the output depends only on the state and it does not really change according to X. Notice that X here is my input. We always show the X on the arc, whereas we show the output inside the state. So if you see the output appearing inside the state, you know that this is a Moore. Okay, this is the state diagram of a Moore sequential circuit. Is this clear? Students? Right. Notice that all the states are reachable. So if we reset, we start initially at state 0, 0. Then you can actually go to state 0, 1. And then from 0, 1, you can go to 1, 0. You can go back to 0, 0. Or from 1, 0, you can reach 1, 1. And then from 1, 1, you go back to state 0, 0. So all of these states are reachable. We don't really have a state which is unused in the state diagram. All of them are used because you have transitions actually toward every state that you have in the state diagram. And for this reason, all of these states are used. Now we can trace a Moore state diagram as shown here in this slide. That bit can be very easily done. You just apply a certain input. You can reset initially, or even without reset, you can actually apply a certain input that will take you back to the state 0, 0. So here, initially at t equal to 0, okay, the present state is unknown. If you don't reset, when you power on a circuit, the initial state, okay, so these are the outputs of the flip-flops, you don't know, okay, so these are unknown. And because the state is unknown, the output is also unknown because the output depends on the state. Now, if you apply the input x equal to 0, now if you are in state 0, 0, this will take you back to 0, 0. If you are in 0, 1, this will take you back to 0, 0. If you are in 1, 0, this will take you back to 0, 0. And if you are in 1, 1, it will take you back to 0, 0. So it does not really matter, okay, in which state you start. If you apply the input 0, this will take you to state 0, 0. So even though the initial state is unknown, once you apply the input x equal to 0, then you know what should be the next state. It will be 0, 0, because in all cases, all the states will take you back to state 0, 0. Now, that was in this specific state diagram. It does not mean that all the state diagrams are actually designed this way. No, sometimes you don't really have the situation, so you have to reset. Okay, but in this specific, okay, state diagram, even though the initial state was not known, by applying the input x equal to 0, you know that all the states will make a transition to state 0, 0. Now, if you are in state 0, 0, then you know that the output z equal to 0. We can tell that directly from the state because it depends on the state only. Now, if you are in state 0, 0, and you apply x is equal to 1, so this will take you to state 0, 1. So notice that here my next state is 0, 1. So if my input x is equal to 1, next state will be 0, 1. If you are in 0, 1 and the input x is equal to 1, this will take you to 1, 0. So notice that you can go to 1, 0. And if the input x is equal to 0, this will take you back to state 0, 0, and so on. So basically, you can actually, knowing what is the state, the present state, and knowing what's the input, you can tell what will be the state next cycle. So cycle by cycle, we make it transitions between these different states. And knowing the state, knowing that you are in state 0, 0, or 0, 1, or 1, 0, the output is 0. Notice the output is 0 here, 0, 0. If you are in state 1, 1, if you reach state 1, 1, now you reach state 1, 1 if you are in state 1, 0, and the input x is equal to 1. So if you are in state 1, 0, and the input x is equal to 1, this will take you to state 1, 1. And once you reach state 1, 1, then the output will be equal to 1. If you are in state 1, 1, and the input x is equal to 1, then this will take you from 1, 1 back to 1, 1. So you remain in the same state, and the output x is still 1. Okay? So this is basically how you can trace a more state diagram. Okay, it's very simple, very easy. You can also draw the timing diagram as shown here in this slide. This is also very simple. So, so starting initially, so even though initially the present state is unknown and the output is unknown because the output depends on the state. So this is shown here, okay, as question marks, or shown maybe in red, okay, depending on your simulator, or shown as X, for example. You apply, notice that here the input x appears just before the negative edge. So here x equal to 0. This is x equal to 1. This is x equal to 1. So look at the value of x just before the edge. And we are using the negative edge because the types of these flip-flops use the negative edge. Okay? So sometimes some flip-flops use the rising edge, some of them use the falling edge. So here, and the author is using a different a flip-flop that uses the negative edge. So for this reason, we look at the input x just before the negative edge. So here it is 0, this is 1, this is 1, etc. Okay. Now, when you apply 0, okay, next cycle at the edge, we are changing the state, okay, from unknown to 0, 0. So it becomes known because regardless of where you start, you are going to make a transition to state 0, 0. And if you are in state 0, 0, then you know that the output is 0. Now, if you are in state 0, 0, and the input x is equal to 1, this will take you to state 0, 1. So this will happen just immediately after the edge, the negative edge of the clock. So the flip-flops and the state is synchronized with the clock. Then if you apply another one, it will be 1, 0. So if you are in state 0, 1 and the input x is equal to 1, this will take you to state 1, 0. You can see that here, okay, etc. So notice that here the outputs are zeros. Eventually, you might reach state 1, 1. Yani for example, here the input is x is equal to 1. Here you are in state 1, 0, and the input x is equal to 1. So therefore, the next state will be 1, 1. And if you reach state 1, 1, then the output will jump 1. So notice that there are no false outputs. There are no glitches because the output depends on the state. It does not depend on the input x, and therefore it is synchronized with the clock, and you cannot really get glitches in the case of a Moore machine. Okay, is this clear? So in summary, what we have done is that we have analyzed clock sequential circuits. What we did is that the first step is to obtain the equations at the inputs of the flip-flops, and then we obtain the next state equations. Now, in the case of D flip-flops, the next state equation is equal to the D input equations because this is the characteristics. This is the characteristic equation of the D flip-flop. So the D flip-flop is so simple to analyze. So when you obtain the equation at the D input, it is the next state. In the case of a T and the JK, what we have to do is that we have to use the characteristic equation of the flip-flop. So first the first step is to obtain the equations at the inputs of the flip-flops. Second step is to obtain the next state equations. Third step is to obtain the output equations. Step number 4 is to fill the state table. Remember, in the case of the state table, first we show the present state. For example, if you have two state variables A and B, these are the outputs of the flip-flops. We show them as the first two columns in the state table. And then we show the inputs. If you have, let us say, one input or two inputs, we show them, okay? And then you show the next state. This is why it's called actually the state table, because it shows the next state depending on the present state and the inputs. You fill the state table. You show the next state according to the next state equations that you have obtained. Okay, so you use the next state equations to obtain, okay, the next state based on the present state and the inputs, and use the output equations to show the outputs. Okay, so we fill here the next state and the output columns, and then the last step is to draw the state diagram. So the whole purpose of the analysis is to obtain the state diagram. So we obtain the state diagram from the circuit. So the circuit is given to us and we are analyzing it. We have seen two different types of sequential circuits. We have seen the Mealy and the Moore, and the only difference between them is how we produce the output logic. Okay, so Mealy depends on the input X, the Moore depends only on the present state. It does not depend on the inputs.